So good morning, everyone. Welcome to the 16th session of memory design course. So before we move ahead, so we are going to start with DRAMs today. But before we enter there, what was we discussing in the last class? Who can tell me?
So we looked upon direct map cache, and then we looked upon fully associative cache.
So we looked at different kinds of caches. Yeah, please continue. Go ahead.
And after that, we look what happens on write.
Okay, बीच में एक और type of cache थी. So we talked about direct map, then we talked about fully associative. There is something in between also. What is that?
Set associative.
Set associative.
Set associative. So what is the disadvantage of direct map?
There are a lot of misses.
Yeah, there can be a lot of misses if you have multiple programs running. Okay, then what is the disadvantage of fully associative?
Area utilization was
Power consumption.
Area and power both. Lot of power gets wasted and a lot of area. The DCAM cell is much larger than the regular 60 cell that we have. Okay, then how is set associative better?
सर वहाँ पे एक पर्टिकुलर लोकेशन को स्टोर कराने के लिए हमारे पास ज्यादा ऑप्शंस थे.
So it is midway
blocks में
between.
divide हो जाते थे.
Yeah, it is midway between fully associative and direct map. In direct map, you could write only at one location. In fully associative, you could write anywhere. But in attempt to write anywhere, we increase the power multiple times. In set associative, we say, okay, not everywhere, but now more than one location you can write to. If it is two-way set associative, we say there are two locations where you could write to. If it is four-way, then you can say there are four possible locations where you could post any of the addresses, any of the data that you want to post. And how to select which one to replace? We talked about that in the last class. See, direct map, there is no question. You just replace anything. How to replace something in set associative and fully associative?
Replacement policy is recently or random.
And what did we observe about LRU and comparing between LRU and random?
LRU had sector logic, but random you don't need logic. But
if we increase the size, then they'll be almost same LRU and random.
Yes, if the cache size is big enough, then LRU and random actually give similar benefit. Then why put an extra logic in coming up to the LRU algorithm? However, if the memory is constrained, then LRU does have a slight advantage over in terms of miss rate over random. And then we looked at the write policy. So any specific feedback and input about the write policy that you would want to highlight today? What kind of write policies are we talking about?
Write through and write back.
Write through and write back. Okay, which one is better? Why?
Sir, actually, I was asking. I didn't get what is actually happening in write through and write back.
So in write through, whenever there is a data update from the processor, L1 cache gets updated and simultaneously L2 cache will also be updated. In write back, and not just L2 cache, even main memory would get updated. In write back, you say that, okay, I have a multiple processor system. I will update the L2 cache and the main memory only when I want to purge this data due to LRU or random replacement algorithm coming into picture, whenever I am removing this data, this particular address location from my L1 cache, that is when I will write it back into the L2 cache and main memory. So in write through, a read access will never result in a write. Suppose processor 1 had an updated data, it would automatically update the L2, and when processor 2 wants to access that particular address, L2 would already be updated. So no write is initiated because of read. Whereas in the write back thing, if for example processor 1 updated the contents of one particular address, then it has just put a dirty bit high in the L2 cache. And then when processor 2 accesses that particular address, because dirty bit is high, you initiate a write operation from processor 1 L1 cache to the L2 cache, and then from the L2 cache into the L1 cache of processor 2. We discussed this last time also. Is this clear?
Yes.
Rohit, your voice is breaking. It's not very clear.
Yes, sir.
Okay. So anything else from the last class? Okay. So there's nothing else. Then we go to today's session. So today we are going to talk about DRAMs. What are DRAMs? What is a DRAM cell?
Single MOSFET with a capacitor.
Why is it called a DRAM? Why is it called dynamic RAM, not static RAM?
It involves charging and discharging of capacitors.
So even in a static RAM, the internal nodes are also capacitors. There's parasitic capacitance there. They get charged and discharged.
But
That
we
is how
need
you
to
store a 1 and a 0.
we need to refresh them here. We cannot
Hmm.
leave them.
So in the DRAM, the way the capacitance charging and discharging happens, refresh is a mandatory requirement. It is not required at all in SRAMs. So you definitely need to have a clock which would come at a regular frequency so that your DRAM contents are refreshed. SRAM doesn't need a clock. आप उसको 10 साल तक कोई क्लॉक ना दो, वो अपने डेटा को होल्ड करके रख लेगा. DRAM can't say that. DRAM में refresh के लिए you have to give a clock every now and then. Is that okay? Now, as already mentioned by one of you, DRAM is denser. It has one transistor and one capacitor instead of 6 transistors in the SRAM. So how does the DRAM cell look like? This is how a DRAM cell is. If you want to write into the cell, what do? You take bit line to the desired level, turn the word line on, and this node will get charged or discharged to the desired level. Now, this C should be small and this M1 should be big. Why?
Charge faster.
Charge?
Faster.
To charge faster, so that the internal node can get charged up very fast. And do you realize that when I turn the word line on, there is actually charge sharing that is happening between BL and INT? Because
Yes,
in
sir.
reality, BL is also a capacitor. है ना? So if this C is very large, then what happens? Let us say this is CBL, and let us say this C storage. It's very large. What happens? The charge sharing would happen, and instead of almost VDD being stored at INT, I will end up storing VDD minus say delta V. And this delta V would be large. Are you able to see this? When this C storage is small, then the voltage at INT will be VDD minus delta small delta V, where minus small this delta V is smaller. Are you able to appreciate this point?
Yes, sir.
Okay.
We are talking with respect to the bitline capacitance, like with respect to bitline capacitance, C should be small.
Yeah. So with respect to bitline capacitance, C should be small means jitna small hoga utna acha hai na.
Acha, yes, sir, yes.
So as small as possible. But there is an opposing constraint also. That opposing constraint is that the B should also be large. But if we come to that, let us first look at how the read operation happens. To do the read operation, the word line would turn on and this capacitor would share charge onto the bit line. And then the sense amplifier turns on and both INT and bit line are discharged. Are you able to see this? So where would the bit line pre-charge be over here?
So can you please repeat this part?
So what part did you understand and what did you not understand? I will then repeat accordingly.
So we were talking about the like the reading, but I got disconnected.
Okay. So when you want to read this particular cell, what do? You turn the word line on.
Yes, sir.
What happens? At once CBL and C store get connected.
Yes, sir. Yes, sir.
Again, charge sharing happens.
Yes, sir.
And you sense which direction the charge sharing is in, and determine if C stored a 0 or a 1 through the sense amplifier.
Yes,
and the
sir.
sense amplifier now discharges both bitline and INT or charges both bitline and INT.
So sense amplifiers, why is it charging bitline or INT? Like why we are talking about the sense amplifier charging bitline or INT?
Yeah, because it arises from my question that I was asking after this.
Okay.
At what voltage will you pre-charge the bitline?
Okay.
What voltage will you pre-charge the bitline? Suppose you want to read a 0. What should be the voltage?
Sir, we can either pre-charge the bitline to VDD or VDD by 2, but VDD by 2 will be even more prominent.
Pre-charging the bitline to VDD by 2 is more promising because then what happens is that when you are charge sharing a VDD from the internal node, then you know that bitline will rise. And when you are charge sharing 0 from the internal node, then you know bitline will fall. So they are moving in two different directions. And you can utilize that to your advantage. Pre-charging it to full VDD, what can happen is that even if INT has gone to some voltage because of charge leakage or whatever, bitline may end up discharging a bit. And that can be a problem for you. You might end up reading that as a 0 instead of a 1. समझ में आया? नहीं. Hello?
So ये वाला point नहीं है.
So आपने bitline को suppose VDD पे pre-charge करके रखा. And then you do a read operation. The internal node had already, due to leakage or whatever, had reached a level of VDD minus 200 millivolts.
Yes, sir.
So in reality, because it was storing a 1, I would not expect my bitline to fall anything. Bitline should remain stable. But because internal node was 200 millivolts lower, bitline falls a bit. Charge sharing would happen.
Charge sharing.
On another node, you had stored a 0. So in that case, the bit line would have naturally fallen much higher. So now the difference between 0 and 1 appears to be like this. Pretty close to VDD, but this has to be considered as 1 and this has to be considered as 0. On
Yes,
the
sir.
other hand, if you were precharging to VDD by 2, then even if internal node has discharged a bit, your bit line would rise. And in case when the 0 was stored, the bit line would fall. This is the distance between the two of them. Okay, and you will see that this margin could be higher. Is that okay?
So can we say pre-charging the bit line to VDD by 2 is much beneficial because the margin is greater?
Yes.
Yes, sir. Yes, sir.
Now comes the third thing, which is called refresh, which means that, see, this internal node would leak over time. Where would it leak? There is a junction capacitance of this MOSFET. There is subthreshold current going through this MOSFET. So many things are happening. So this internal capacitance would leak, int node would leak. And what you want is that to restore the cell content, suppose it has leaked by 200 millivolts. If you do a read operation right there and then what happens? This will still be read as VDD, and I will restore VDD value onto int node. So this is called as dummy read. This is not a user triggered read. This read happens anyways, so that the contents of the DRAM are maintained. This is the refresh part. And to increase the duration between these dummy reads. So do you realize that when the dummy read is happening, actual read cannot happen? So your DRAM is unavailable for use. The customer or the user is waiting until your dummy read closes. Only then a real read can be initiated again. So you want to increase the spacing between dummy reads because that reduces the unavailability of your DRAM. For this, you need to reduce the leakage of INT node. To reduce the leakage of INT node, there are two ways. First, keep M1 to be very small. Second, if you cannot keep M1 to be very small, or even if you are able to keep M1 to be small, keep C to be as big as possible. So that even if some charge leaks out, the dip in the voltage level is not very significant. Instead of 200 millivolts, only 100 millivolt dip is coming. So now you can double the duration or double the interval between two refresh cycles. So while in the first slide, earlier slide, we had said that M1 should be big and C should be small. That was what we had said there. Over here, we are talking about exactly the opposite thing. Are you able to see this?
Sir, why should we increase the storing capacitor C?
Because if, let us say, I leak is the current that is leaking. If the capacitor is large, then it will take extra time for the voltage on this int node to fall. So restoring the value of int node will be easier. See, the threshold is int node should not fall below 200 millivolts or 300 millivolts. So the duration it would take for int node to fall for the same leakage current will be higher if the capacitance is larger.
Okay.
So you can increase this interval then.
Okay.
So these are contradictory requirements on the capacitance sizing and the M1 sizing. Are you able to see this?
Sir, but increasing the capacitor will increase the access time, sir.
It will increase the access time. Why do you say so?
Because
If the
ultimately,
capacitor is large, it will charge the BDD by 2 of bit line higher, much higher or much lower. So capacitor large means that it will actually help your read operation also.
sir, it will be able to store large charge. I accept that. But the RC constant will increase also. Ultimately, the time required to read will increase.
Oh, okay. So see, you finally would have the sense amplifier driving the bit line and the internal node. Only one internal node is going to be visible to the sense amplifier. This capacitance is 100 femtofarad, let us say. This capacitance is 5 femtofarad. So 100 की जगह 101, it appears as 105 femtofarads. Not a very big deal, no?
Suppose if we want to say that to reduce the leakage, we are increasing the capacitor which is storing the contents. So then it will go. It can increase only by 2 magnitudes.
So you do not, So you do not reduce leakage by increasing the size of C. Be careful. You just increase the interval between refresh. Leakage here you can reduce only by reducing M1. By changing the size of C, by using a larger C, you are just increasing this interval between 2 refresh cycles.
Okay.
है ना? Leakage को तो कोई impact नहीं आएगा. Leakage will not change because you used a larger C. In fact, leakage would only increase because the higher a higher VDS will remain for a longer duration of time.
Okay.
So leakage will probably only increase, but you increase the interval at which you will do the read operation, dummy read there.
Okay, sir.
So we are calling this dummy read, like the refresh as dummy read, right?
Yes.
Okay. Okay. Sir.
We're calling it as dummy read because no one asked us to read it. This is just being done.
Yes, sir.
Yes, sir. The other node of sense amplifier remains, the reference bit line remains as VDD by 2 only, right?
So the sense amplifier, what does the sense amplifier do? It will amplify the difference between bit line and bit line bar to full VDD and ground. Is it not?
Yes, sir.
So the bit line would go to full VDD if that was what was required, or it will go to full ground if that was what was required. As bit line goes to ground, the internal node will also discharge, or as it goes to ground, the internal node would charge up. Is that clear?
Sir, how we will generate actually VDD by 2, sir? Because really supplies a VDD.
We will come to that. So we आगे जब मत करो, जहां तक बताया वहां तक is it clear?
नहीं सर, और रिफ्रेश में सर जो रीड बोल रहे हैं, तो रीड तो सिंपली रीड कर लिया, रिफ्रेश समझ में नहीं आया, रिफ्रेश में हो क्या रहा है?
Refresh is also simply read.
Read
We're just
तो
calling it dummy read because it is not triggered by the user. It is simply read. Row by row, you read every row. What happens? All the cells get refreshed. All the cells are written back into.
Sir, it is a power wasting field, sir.
Yes, DRAMs consume much more power than SRAMs.
And
but they
sir,
are much denser. But they are much denser. आगे बोलो.
रिफ्रेश का मतलब क्लियर नहीं हो पा रहा है, कर क्या रहा है? रीड तो ठीक है, रिफ्रेश रीड सेम है आपने बोला, बट क्यों ऐसा हो रहा है?
So what do you understand by the term refresh when we talk of DRAMs? What do you understand? I'm not saying that your understanding may be correct or not correct. What do you understand as of now?
रिफ्रेश सुन के मेरे को यही लगता है कि सर सम वोल्टेज वी हैव टू रिगेन करना होता है, उस वोल्टेज पे दोबारा चले जाओ काइंड ऑफ थिंग.
So you want to replenish the charge onto the internal node.
Okay.
Whether it was a 0 or a 1, you want to bring it back to the original level. Am I right?
Yeah, ताकि हमारा डेटा लॉस ना हो.
ताकि data loss ना हो.
Yes.
So during read operation, what happens?
Internal node discharge होगा according to bit line voltage.
Internal node would share charge with the bit line.
Yeah, share
it
charge.
May get charged up or it may remain low.
Yes, sir.
So what happens?
either internal node will decrease by some voltage delta V, or it will be a very less voltage.
It will either decrease by some voltage or it will increase by some voltage.
Yeah.
I know. And then you activate the sense amplifier. What happens? Bit
Sense
9 goes to
amplifier,
0, and as a consequence, even INT goes to 0.
bit line goes to 0, INT. Yes, sir. Yes, sir. Going to 0. Yes, sir.
So you were reading a 0. When you
Hmm.
initially connected the bit line and the internal node also rose to VDD by 2 minus delta
VDD
because
by
of
2
charge
minus
sharing.
delta.
Because of charge sharing.
Yeah. क्योंकि
Now when you
इसमें
activate the sense amplifier, bit line goes to 0 and simultaneously INT also goes to 0. So whatever loss of charge had happened, you replenish that charge.
okay. Yes, sir.
Okay? And that is
So-
why it is called refresh. You refresh that charge.
Okay. So every read will do this kind of mechanism in itself.
So this is how read happens.
Okay, sir.
But for refresh, even if a read operation is not triggered by the user, you will do dummy reads. Every row you will access once every 1 millisecond.
And okay. Yes. Got it.
ठीक है ना? Anything else?
Sir,
Sir, how does
okay, you go first.
Yes, Malika.
Sir, how does increasing the size of the capacitor lead to increase in the dummy read duration?
Interval.
Yeah,
not duration.
interval. Yeah, interval.
So you tell me, sense amplifier has a offset dependent on voltage, that I want
Yes.
my the voltage to be at least this much there so that I can sense a 0 or a 1.
Yes, sir.
So, and we are saying capacitor will leak charge through M1.
Hmm.
So voltage is Q is equal to CV.
Mm-hmm.
So Q by C is the voltage. If you increase the charge that you can store on the capacitor,
Hmm.
then even if the same current is leaking, the delta V would be lesser because
Yes.
the
Mhm.
capacitance is larger.
Mm-hmm.
So sense amp required a particular delta V. Now that delta V is lesser in the same duration, so you can actually let it discharge for some more time
Okay.
and then do the refresh.
Mm-hmm.
So that is how a large capacitor helps in increasing the interval between two refresh cycles.
Okay, sir.
ठीक है ना?
Mm-hmm.
Anything else?
Sir, I understood why we are refreshing, but can you please explain how we are refreshing the internal node?
We simply read. We simply read every row.
Okay.
So when you read a row, what happens? अभी हमने बात करी.
So charging or discharging.
Sense amplifier will fully charge or fully discharge the internal node. So any
Yes.
loss of charge which could have happened because of leakage is taken care of.
Okay. Okay.
ठीक है ना?
सर जस्ट फॉर क्लैरिफिकेशन, जो इंट नोड है सर उसका स्विंग अपन 0 से VDD ले रहे हैं, वोल्टेज स्विंग से.
आप बताओ. Good question. Very good question.
क्योंकि सर
What do we have there? Bit line को int node से क्या चीज connect कर रही है? Is it a transmission gate or a NMOS?
डायरेक्ट ट्रांसमिशन गेट तो नहीं बोलेंगे ना सर.
Pass gate है ना ये तो.
यस सर.
This is pass transistor logic.
यस सर, पास ट्रांजिस्टर. या
So what is happening here? What would be the?
Sir,
Can I transfer a VDD to int node like this?
No, sir.
गेटेड सर. मतलब सर अगर बिट लाइन को VDD by 2 पे ले लिए और रीड ऑपरेशन सर अगर कर रहे हैं तो 0 इंट पे अगर है तो चार्ज हो जाएगा. समथिंग नॉट क्लियर कि क्या हो रहा है सर. इंट नोड रेंज क्या हो रहा है वोल्टेज.
नहीं. If you just try to work it out, what did we say? That I have my bit line at VDD by 2. Let's go to the read wala slide again. I had my bit line at VDD by 2. When the internal node got connected, I discharged a bit, and then sense amplifier ensured bit line went to 0. And as bit line went to 0, because this is on, this also goes to 0. This is simple.
Yes, sir.
Now, if int node stored 1, what would happen? Bit line would rise. Then
Yes, sir.
once the sense amplifier turns on, it will take it to 1. Now this 1 on the bit line needs to transfer to int node. How would you do it?
So WL high करके
WL हाई ही रहेगा.
WL हाई रहेगा, वर्ड लाइन हाई है, लेकिन ये तो NMOS है.
Yes, sir.
तो NMOS
Sir,
कितने?
there will be a VT drop.
तो VDD minus VT जाएगा.
Yes, there will be a VT drop. Now, if you do not want a VT drop, what do you need to do?
So pass gate.
पास गेट तो लगा ही हुआ है ना अभी.
Sir, charge the capacitor.
How? That you anyways are doing, na? You anyways are charging the capacitor from the bit line. You are sending charge through M1 to INT node.
Transmission gate. Sorry, I said pass gate. Transmission gate.
Oh, so then it's kind of double the area.
हाँ, yes sir. हाँ.
Can you do something else? Think of assist schemes that we used in SRAMs. Can you do something like that over here? What did the assist schemes do?
Sir, can we have WL at VDD plus VTH?
Yes, so we can overdrive the word line. If we overdrive the word line, what happens?
Sir,
Yes, sir. Then VDD will
VTH drop will be compensated.
Yes, the drop gets compensated. ठीक है? Is the refresh operation clear now? If you take word line to a level which is higher than VDD, I can compensate for the VT drop that could happen because of the pass gate. Therefore, DRAMs would have some charge pump that would raise the level of word line to a value which is higher than regular word line. Okay. Any questions? Okay. So if this is clear, that is memory, the DRAM cell operation is clear. Then we look at in terms of refresh overhead. See, we said that refresh needs to happen at a regular interval. So because leakage goes exponentially with temperature, the refresh rate can actually go very high at high temperatures. Okay. What is happening? That you count through all the row addresses once per refresh interval. And in that duration, the memory cell contents are refreshed. What this means is that in that duration, when you are kind of reading these, doing dummy read on the memory array, in that duration, you cannot do another operation. Because read is happening, you cannot now do any other read or write on the DRAM. So the DRAM is unavailable during the refresh period. Are you with me? Are you able to see this?
Yes, sir.
And this also gives a brief quick calculation of that. If the if there is a 8192 cross 8192 array and every excess is 10 nanoseconds, so how much total time is given there is lost in refresh? So that overhead is also being calculated. Is that okay? Any questions?
Sir, what is this 10 nanoseconds, sir, exactly? Read time for SRAM cell or like we need
We're
a
not talking about
like base
SRAMs
for
now, no? We're talking about DRAMs.
no, we need a base for comparison, no, sir, between those both so that we can say which one is better. So what is
Sorry?
this 10 nanoseconds?
No,
We need
what
a
do-
base to compare SRAM and DRAM, right?
no.
So
When I'm storing data in a DRAM, who's talking about SRAMs?
okay, so this is only for DRAM then. So what is this 10 nanoseconds, sir, exactly?
What do you understand by read time?
I mean, without the refresh, only I'm like only regarding the read time.
What is read time according to you?
So I mean, sir, the read operation should be completed. I'm like from the starting from the word line to the end where we
Yeah.
read the capacitor value. So
Yes.
I think that should be the read time.
Yes, exactly. That is what it is.
So we don't have the refresh time in this.
Is refresh
included
time
in that.
different from read time? What did we just say? Refresh
Okay.
is equal to dummy read.
Yes, sir. But yes, sorry. Yes, sir.
Read time is the refresh time per row. Per row. So you need to see how many rows are we talking about. How many rows are we talking about? 8192 rows in this example. So 8192 times into 10 nanoseconds upon at what interval? It's at 3 milliseconds interval. So 3 into 10 raised to the minus 3 into 10 raised to the 3. And finally we get the percentage overhead. Fine. आगे बढ़े?
Yes, sir.
Okay. So now we look at how this capacitor is designed. See, we are saying that there is one transistor, one capacitor in the DRAM cell. How do we make the capacitor? So let's look at this thing over here. Over here, word line is running in the polysilicon. So word line is taken care of. Bit line connects to one edge of the one terminal of the like one either source or drain of the NMOS, and the other side has to have a capacitor. That capacitor could be made by using poly, having a little dielectric in between, and then again putting some poly. So how will this look like in a screenshot? Something like this, where different, what do we say, where the polyfin structure has been used so that overall capacitance is higher. This represents, the blue one represents the bit line, source drain region. The pink one is the capacitor. The green ones are the other plate, other side of the capacitor. This is the poly gate. Is this clear? Are you able to see this?
So this structure of poly is making them in parallel, so to increase the capacitance.
Yes. So you're going vertically, you're adding fins.
Yes.
So that in the same area you are able to implement a much higher capacitor.
Okay. Okay, sir.
Okay. So this is how this could look like in a bigger setting, where the capacitor could actually be made. So over here, and the bit line is over here, and the capacitor is now made between somewhere above, far above, metal 4, metal 5 के बीच में you make these capacitors. Is that okay? Capacitor can be implemented in two ways. In the previous one, we said it is right there at the poly, so much below metal 1 itself, whereas it can also be implemented by a metal and metal capacitor. So MEM capacitor, where the poly, the plug on the source drain actually comes to a much higher voltage level, a much higher metal level, and over there this dielectric is added. So this is called as capacitor over bit. There are other ways to make capacitors. So capacitance over bit we just saw. The fin capacitors we also just saw. We will just look at TENS capacitors. TENS capacitors, what do they involve? They involve us digging a trench into the silicon substrate. And when that is done, I deposit a very thin line of dielectric there, and then I fill this with poly again. So now in the TENS capacitor, you do not even need to go up high up and do not need to waste area and due to contacts and vias or anything like that. The TENS can be designed right there inside your memory cell, right next to the source drain region. It can be connected like that, just like this. You see the trench is connected to the transistor source drain region. Any questions?
So the trench one is less complex while designing.
Yes.
Okay.
The trench one is actually complex in designing, and you see this is how the DRC is defined. The aspect ratio, if I keep the trench to be wide, I can go very, very deep.
Yes, sir.
My capacitance can be large. If I do not want to give, but I lose area. If I do not want to give area, then due to the very nature of it being a trench, I go to lesser depth and my capacitor reduces. This is intuitive. When we wanted to use larger capacitance, we were ready to probably give more area also. But it is important to understand that if area is the primary thing, then you can do something more about it by doing away, for example, with the depth. Is that okay?
So area is the main concern over here. Like,
yes, you reduce the area, you therefore end up reducing the depth and the capacitance value.
Yes.
The amount of capacitance. So area and capacitance are a direct head-to-head trade-off. So what did we look at till now? That the capacitor should be big. If the capacitor is big, I can do faster, more robust read. I can reduce refresh requirements. I want to keep a big capacitor, but I want to reduce the area penalty. And see, if the capacitor is big, what happens? To discharge or charge the capacitor also takes longer. So write time also increases, but we somehow should ensure that write is non-timing critical. How do we do that? We already talked about word line overdrive. We talked of it in terms of ensuring that there is no VT drop at the store node. But in reality, when you do word line overdrive, you also speed things up a bit. So write operation should not be timing critical. Only read operation should be timing critical. So if I want to reduce area, then capacitor becomes smaller. However, bit line capacitance either remains same or increases. So bit line capacitance per bit cell. So the reality is that as the scaling happens, I should use bigger capacitor. As I go to more finer geometries, I need bigger capacitor, but the density requirements of the advanced technology would limit me to use a smaller capacitor. In advanced technologies, trench capacitors therefore are limited because the trench capacitors try to reduce area. Try to reduce when you want to reduce the area in the trench capacitors, the capacitance value reduces, but you want to increase the capacitance. So the metal capacitance or the capacitance over bit is more promising for advanced technologies. Is that okay?
Yes, sir.
When you use metal in metal capacitor, there are more steps involved. More steps involved means more defectivity can come into picture. There can be yield loss. Otherwise, there are, any decision that we make also has an impact on speed on performance improvement, not just area. So all these three things have to be kept in mind when we are deciding which kind of technology to go for. Now, if you're going to join any circuit design company, then it doesn't make a difference because this thing will be decided for you by the company itself. But if you're going to join a company which does not have its own fab and does not have its own capacitance creation process, then you have a choice whether you want to go to TSMC or Global Foundries or ST or someone to choose the technology. And it is for that this discussion is relevant for you. Okay. So until now, what we have seen is that DRAM cell is based on capacitor storage, which is non-regenerative in nature. It has very high density to boast of, gigabits per centimeter square. And there is, therefore, for imaging processors, graphics processors, or multimedia processors, there is a huge on-chip DRAM also that we are talking about. However, there is a challenge in scaling the DRAM capacitors, and the parasitics become more and more important as we go to advanced technologies. So speed takes a hit, especially in the morning hours. The speed takes a hit, And okay, for DRAM, you definitely need periodic refresh. Is it clear till here?
Could you once again tell why the yield loss was coming in the picture in last slide?
Why the?
So about the yield loss.
Yeah, so the more the number of fabrication steps involved, the more the probability that there will be some misalignment or some extra defectivity that will come into picture. Since the stem of the DRAM capacitor, the MIM capacitor, needs to be built across multiple process steps, multiple layers. Anywhere, if there is a misalignment, there could be a loss in yield because of some resistance or something that comes into picture. Is it clear?
Yes, sir. Thank you, sir.
Sir?
Yes.
Sir, word line overdrive, is it done only when the VINT is high? Like if one is stored only, then word line overdrive is done, or is it done for all cases?
So can you tell that in a particular row you will store all the ones? Or do you think there would be zeros?
Yes, so that was the question. Like, is there a...
So if it is a common word line, whether you are storing a 1 or a 0 doesn't matter. The word line is being overdriven.
Okay, sir.
So what does that do? That ensures that you can keep M1 to be smaller. So you keep M1 small, you save area.
Yes, sir.
Okay. So what have we done till now? We looked at the memory array. Like we looked at the memory cell. Now what we will do is we'll look at memory array, DRAM array a bit, and then we will take a quick look at let us say sense amplifier, reference and sorry. So what I was saying was that we will now look at the memory array, and then we will look at sense amplifiers, reference generators, row decoders. You already know. We will not really spend time on that, but we will look at word line driver in terms of charge pump. Okay. I'm not sure if we will spend time on data bus amplifier or voltage regulators because they are completely different topics and can take a lot of time. But I will definitely introduce you to the first few peripheral circuits which are different from SRAMs over here. But you do not assume that we are covering entirety of DRAM in our class. There are other circuits which go into DRAMs which you may want to study in your analog design courses or mixed signal design courses and so on. Okay. So this appears to be the same as a SRAM array. Am I right? You have multiple cells, rows, columns, then column selectors, row decoders, everything. This appears to be the same as a regular SRAM array, except there is one difference, that it is always a square. The number of rows is equal to number of columns in a DRAM. Why do you think this is required? Or why do you think this is done? Tukka maro.
To have same cap on word line and bit line.
I did not say that the width of the cell is same as the height of the memory cell. I just said number of rows is equal to number of columns. I also did not say that the drain capacitance is equal to the gate capacitance. I just said rows is equal to number of columns.
Address decoding bit कम use हो might be.
Sorry, दोबारा से बोलो.
Address decoding bit कम use हो might be मतलब कि हम एक ही लेकिन
So actually, very, very close. So what happens is, let us say we had a 4 megabit DRAM. So you have 2K cross 2K array. And so 4 megabit के लिए कोई एक bit access करने के लिए you would otherwise need 22 bits. 22 address bits. That is a huge address bus. Hello? So there is a huge, very big address bus, 22-bit address bus that we are talking about. To be able to give that kind of bandwidth, that many number of pins is not possible when you have off-chip DRAMs, or you do not want to route too many signals. So DRAMs therefore say that, okay, we will organize our data such that 11 bits are used to decode the rows and 11 bits are used to decode the address, the columns. What we will do is we will first send 11 bits of row address, then we will send 11 bits of column address, and then I will be able to read one particular bit from this array. This is row address, this is column address, and then I will be able to get this data on the queue bus. Are you able to see this?
So what's the benefit of sending 11 and 11? Like, are we using less resources?
Yes, your bus width is now 11 instead of 22.
Okay, okay. So, but the what about the power consumption? Like, power
What
overall,
about?
the power consumption will be same, like 11, 11, 22 ही कर रहे हैं. But at an instant, the power consumption is reduced by half.
Yeah, that's okay.
Okay.
That's okay. Finally, you are using much lesser resource in terms of area.
Yes.
है ना? What have you done? You've, instead of reading the entire, getting your bit in one go, you are getting it after 2 cycles. Not exactly 2 cycles. So what we call as read address strobe. We call this as read address strobe, RAS, and we call CA को latch करने के लिए we come up with what is called as CAS. So there are these two signals, read address strobe and column address strobe, which define whether I am giving a row address strobe, and column address strobe, which define whether I am giving a row address or a column address. Okay. So if I want to have a 16-bit DRAM, I will have multiple pages, multiple pages to get to this 16-bit interface. If I call this as a, इसको block कर देते हैं. So let us call this as one array or a block. So one block gives out 1 bit. If I have 16 blocks, then I would need 16 bits at the output. So this particular memory is organized as 512 rows and 512 columns. So 512 rows, 512 columns for 4 megabit capacity, and I have 16 bits. So I go to 16 such pages: 1 page, 2 page, 3 page, 4 page, and 16 such pages. Is that okay?
Sir, can you repeat this point? Okay, so 16-bit है.
Okay. पहले इसको वो देख लेते हैं, क्या कहते हैं, logically देख लेते हैं. Do you realize that in this one page or one array, I could read only 1 bit?
Yes, sir.
Yes, sir.
So if I have an 8-bit word, I will have to have 8 such circuits there.
Yes, sir.
So if I have a cross 2 DRAM, there are 2 such pages. If I have a cross 4 DRAM, 4 such pages. Cross 8 DRAM, 8 such pages. Banks. Let us call them as banks. Is that okay? Hello. Whatever is your bit.
सर पर बैंक से अपन पहले में 2 बिट निकाल रहे हैं और 4 and 8 बिट ऐसे सर.
Yeah, because there are 4 such pages. There are 4 sets of sense amplifiers. There are 4 sets of data buffers. Row decoding could still be common because सारे pages पे same ही row जाना है, सारे pages पे same ही column select होना है. So row and column decoding could still be common. I have not repeated them. You notice this?
Okay. Yes, sir. Yes, sir. Yes, sir. यही सर number of bits down हो रहे हैं.
Yes.
Decode करने.
However, in a real implementation, you may need to have row decoders again and again. You may want to share them across multiple blocks. So over here, logically, I could share them across all the blocks. But physically, that would mean a lot of capacitances, a lot of RC to handle. So I could repeat So row decoders 4 times instead of 8 times. Column decoders 4 times instead of 8 times, because I could share those column decoders across 2 different pages. Are you able to see this now? All
Yes,
these
sir.
row decoders actually get the same row address. All the column decoders will get the same column address. And therefore, you could share them across multiple banks. Is it clear now? Hello? Any questions? So this is very different organization than what you have in the SRAM. That is why I'm spending some time on it. I will not spend times on those structures or parts which are exactly the same or very similar to how we have in the SRAM. But you do realize that this is a very different topology or very different memory organization. So it's important that you understand this well. Is that okay?
Sir,
Hmm.
sir, if there is a 4 mbit cross 4, then we will just take 1024 cross 1024 memory array and 10 bits each to decode.
So if it is 10 cross 4, then I would probably have just one block over here. इसके अंदर 4 पेजेस आ गए, मेरे 4 बिट्स आ जाएंगी. But since it is okay, since it is 4 megabit total capacity, and upon 4, I would say that each of these things would be 256 k bits. So 1k cross 1k के आपके 4 सेट्स बनेंगे. You are right.
Okay,
अभी यहाँ पे 512 क्रॉस 512 के 4 सेट्स हैं. अगर ये क्रॉस 4 में बनाया गया होता तो 1k क्रॉस 1k के 4 सेट्स बनते. You're right. एंड एक ही इसमें आपका काम चल जाता, एक ही ब्लॉक में आपका काम चल जाता. Is that okay?
Yes, sir.
So a logical way to, or the logical diagram of this appears something like this. There is a read address trope, there is a column row address trope, column address trope, write enable, output enable, and then address bus and data bus. Okay. Now, since you, at any given point of time, you will either read or write into the DRAM. What have you done? You merged data buses into one. And we already discussed about how RAS and CAS signals are used to merge or reduce the width of the address bus. Is it clear? In an SRAM also, you would either use the Q bus or the data bus, but you do not make that kind of an effort because SRAMs are always embedded. DRAMs are usually main memories. They are off chip. So there is a very strong constraint on number of pins that you could have for the DRAMs. And therefore, everything is done to reduce the pin out of the DRAM there. Any questions? Okay. No sound means no questions then. So 256k words, 512 cross 512 array. This is the logical diagram of this memory, you may say. Okay. This is logical diagram of that memory. And 512 bits are read out per page. We could say there are 16 pages. So we kind of match that particular memory that we had. And subset of bits are returned to the CPU. So the column decoder, there are multiple column decoders, and then the subset of these excesses are reported to the CPU. The key timings that are linked to a DRAM: TRAC, which is minimum time from read address strobe to data output. TRC, which is minimum time between one read address strobe and another one. Okay. So in addition to whatever time it takes for memory to give out data, TRC also involves pre-charge of the bit lines and reset of the memory circuits there. So TRC is greater than TRAC. Okay. And then T column address strobe, or TCAS, is the minimum time from CAS to valid data. Now notice that if TRAC was 60 nanoseconds, this is much lower. Why? Because now sense amplifier output is already there. All that you need to do is do some address decoding and select which bit to give out. Whereas for the first timing, you not only had to do the decoding of the row region, that is the row decoder, but also discharge the bit line, activate the sense amplifier, and then give an output. So TRAC is therefore greater than TCAS. Okay. And then TCC is the minimum time from the start of one column access to the start of next. What do you think this would involve? Why do you think there is this extra gap between TCAS and TCC? What extra stuff would be involved there?
Refresh.
No, refresh तो आपने जब read करा तो हो गया, हाथ के हाथ ही हो गया था. What could be the extra stuff involved there?
Charging of bit lines.
When you change the column address, when you change the column addresses, bit lines are not even being touched. Sense amplifier operation has already happened. It is more about resetting the state machine. Resetting the state machine so that the new decoding can now, resetting the latches, everything, so that the new decoding can now start.
Basically settling down.
I'm sorry?
Basically settling down.
Yes. Now, there are two kinds of reads that could happen in a system, in a DRAM. We call them as early read or late read. What does that mean? So let us look at it over here. So you gave row address strobe, and row addresses were put on the bus. Sense amplifiers were operated, and something was done on the sense amplifiers. Some output is latched onto the sense amplifiers now. After some time, you give the column address strobe, and after the column address decoding, some output can be made available on the output bus. What has happened? Even while you were still reading the rows, output enable had gone to low. So as soon as column addresses or sense amplifiers are selected, the output can come out on the D out bus. So there is one kind of timing over here. This is called as early read, where output enable was already low. There was no decision making done at that time. In late read, what happens is, much after column address has been given, so we assume that output was actually available in the memory, but output enable went low much later. In this case, as soon as output enable went low, data out will appear much faster. So you see this duration is much smaller than this duration, CAS to okay. This is called as late read. Abhi, you're not probably able to understand what is the benefit of late read, but when we will talk about architectural ways to recover speed or recover performance of DRAMs, then this concept of early read and late read will come into picture. So just keep this in mind that there are two kinds of reads, early reads and late reads. And I tell you that over here, since the bus is in high impedance zone for a large part of the time, the bus could be used by something else. That is the hinter there. Okay. And then you do the late read. Is that okay? Early read, late read में फर्क समझ में आ गया? Is that part clear? Friends, we are not in a physical class where I could see your faces and know if you have understood or not. We are still in an online class.
Sir,
Yes, please ask.
sir, why did column? I sorry, sir, I do not understand. Why did column address came first? Sorry. Okay, okay. I am looking at it wrong. My bad.
Column address came at the same time. Output enable was low earlier, and in the other case, output enable came low much after the column address or CAS had come.
So why was the enable later in second?
So that is what I said. The reason of this why we will talk about later. But do we
Okay.
understand the functionality?
Okay.
There
Yes.
is a benefit of this. We will talk about that later. But do we understand the functionality part of it? Huh? There are two different timings. One timing is much shorter than the other timing. Okay.
Yes, sir.
Similarly for write, there could be early write or late write. In the sense that the data could be latched. The data could be latched as soon as it appeared and the column address appeared, or as soon as CAS came, or the write operation can start right away, or data could be latched and write operation would start later. Because again, for some reason, we will talk about that reason later. But just like for over there, we had the dependence on arrival time of OEL. Over here, we have the dependence on arrival time of WEL. Okay.
Okay.
So now how do we access the DRAM? So there is a CPU. It sends information to the memory controller. Memory controller then sends information to the DRAM. How does it do? It first sends the address and the read row address probe. Then it sends the address and the column address probe. When it sends the column address probe and the address, the information from the sense amplifiers comes to the data in-out buffers. This is then sent back to the memory controller, and then that is sent back to the CPU. So if you look at it in terms of timings, so there is this first timing called row command delay, TRCD, which means the row decoders were activated, memory was the bit lines discharged, and something was latched onto the sense amplifiers. Then you do TCAS, in which the memory controller sent the address to the column decoder, and then the sense amplifier sent back the output to the memory controller. That is TCAS. TRAC is equal to TRCD plus TCAS. Are you able to see this? Any questions? Because RAC meant when you gave the row address strobe to the time when the output was available on the output bus. That means TRCD plus TCAS. Then you need to give some time for pre-charging of the bit line. Let us say that is T3. So this pre-charging of the bit line happens after TRCD or TRAS, and therefore the next row command can be given after bit lines have been pre-charged. So TRAS plus T pre, that is TRC. This is also called as row cycle time. Is it okay? Is it clear till here? Any questions? Okay, no questions. So we've looked at multiple timings until now, TRCD, TCAS. So this is the time which is the shortest time. Do you realize that this is the fastest that your DRAM can give output? So this is the time that is given, talked about in the ads, that this is the fastest DRAM that we have, and so on. TRC is something that embedded system designers and DRAM manufacturers know is important. And for a computer architect, you're not really bothered about when I can do the next row access. What you're bothered about is I had a miss. How quickly can you give the output to me? So TRAC is what is of interest to the computer architect there. Is that okay? Any questions?
So you said that the charge is done while reading only. Why is it a separate component here?
So pre-charge is done after the sense amplifier information has been given out, and you no longer need the sense amplifier output, है ना? तभी आप pre-charge शुरू कर पाते हो. So it has to be a separate component ना, मतलब RCD के अंदर तो नहीं आएगा ना वो.
हाँ, technically तो नहीं है. मुझे लगा ठीक है. Got it.
है ना? It cannot come in RCD. Okay. So in terms of latency, how much time it actually takes from the CPU to this, you will see that depending on what operation we are talking about, whether it is only CAS, column address strobe that is required, or row address strobe and column address strobe both required, or you need to access two different rows, therefore pre-charge also required. Based on that, E1, E2 or E3 will be used, but in reality, there will be lots of delays. First you will put transaction request into the queue, then it goes to the memory controller, then it goes to the command sequencer, then it goes to the command is sent to the DRAM, then DRAM takes its own sweet time, the ones that we talked about, and then all this information is sent back to the CPU. Do you now realize why access to the main memory could be of the order of microseconds or hundreds of nanoseconds? DRAM doesn't take that much time by itself, but there are so many additional transactions that need to happen that it takes a lot of time. Are you able to see this?
Yes.
So when you talk of a DRAM and performance of a DRAM, if you just focus on this part, it may not really change the system performance significantly. If you really want to improve the system performance, you have to look at all A, B, C, D, E, and F, and then see whichever is dominating and reduce those timings. Is that okay?
Yes, sir.
Yeah. So let's just take one sample. वही जो हमने पहले sample लिया था. 60 nanoseconds is the TRAC. 110 nanoseconds is the TRC. Column is 15. Then time between column accesses is 35. But in practical, as we just said, there are so many other things that come into picture. This 15 goes to 40 to 50 nanoseconds. Okay? And then because IO का भी time आ जाता है, and then in reality that 40 to 50 or whatever becomes 180 to 250 nanoseconds latency when it comes to the processor part. Is that okay? So that A, B, C, D, E, and F. So A plus B plus C plus D plus F is a huge amount. Could be anything between 120 to 180 nanoseconds. Whereas your memory TRAC is at 60. Is that okay? So we'll close our class here. We'll start from we'll kind of start from a quick review in the next class. Okay. So I'll stop the recording. Thank you guys. See you on Tuesday then.